Swayam Prabha. Digital India. Educated India.
Good morning, everybody. Today we will discuss about one-dimensional steady-state conduction in various geometrical configurations. Let us consider a plane wall with uniformly distributed heat source. In the last lecture, we solved heat conduction equation in a plane wall. In this lecture, we'll again consider a plane wall, but with uniformly distributed volumetric heat source, which is Q star. And this wall is such that its variation in x direction, temperature variation in x direction will be considered. In y direction, it is extended to infinity, and z direction, that is perpendicular to the plane, it is extended to infinity. That means at any z, we'll get the same distribution repeated. And at x equal to positive L, the local ambience is such that its temperature is T infinity and the film heat transfer coefficient is H. Similarly, at x equal to minus L also, the local ambience is such that its temperature is T infinity and the film heat transfer coefficient is H. Now, governing equation for heat conduction problem d2t dx2 plus d2t dy2 plus q star by k equal to 0. Since we have dispensed with y direction variation and z direction variation, the governing equation is d2t dx2 plus q star by k equal to 0. If we integrate once, we get dt dx equal to minus q star by k into x plus c1. Integrating again, we'll get t equal to c1x minus q star x square by twice k plus c2. Now, boundary conditions are at x equal to minus L, say we can call it Ts1, at T temperature is T equal to Ts1. Although we have written here S, let us call it Ts1. And at x equal to plus L, T equal to Ts2. As if Ts1 and Ts2 are different, although here it is same, we'll see, if they are same, what will be the result. But more general picture is obtainable if we consider at x equal to minus L Ts1 and x equal to plus L Ts2. So if we substitute in equation 1 x equal to L condition and x equal to minus L condition and x equal to plus L condition, from there we'll be able to evaluate C1. C1 will get Ts2 minus Ts1 by twice L. Having found C1, if we substitute C1 in equation 1 and for the condition x equal to plus L, we will be able to evaluate C2. C2 will be x star L square by twice k plus Ts1 plus Ts2 by 2. And then the general solution for temperature Tx is q star L square by twice k into 1 minus x square by L square plus Ts2 minus Ts1 by 2 into x by L plus Ts1 plus Ts2 by 2. So this is a very simple solution. We have got temperature distribution when we have uniformly distributed heat source Q star present in the material. Next, we will assume Ts1 and Ts2 are same, which is equal to Ts, which is basically, our figure shows also that. So, Ts2 and Ts1 both are same, equal to Ts. Then expression for temperature distribution Tx becomes little more simple, because this Ts2 and Ts1, they are same, it will get cancelled out, and this Ts1 and Ts2, they are same, twice Ts by 2, it is Ts. So we will get Tx equal to q star L square by 2k into 1 minus x square by L square plus Ts. The maximum temperature is naturally at x equal to 0, and this will be defined by T0 is q star L square by twice k x equal to 0, so plus Ts, equation 4. A common situation is one for which it is the temperature of the adjoining fluid is known. We have already mentioned about it, that is T infinity. And in such a case, from the temperature distribution, if we find out the temperature derivative, that is minus k dt dx at x equal to L, this will be equal to H Ts minus T infinity. That means whatever is the energy amount of energy conducted minus k dt dx at x equal to L, that will be convected. So we can write minus k dt dx at x equal to L equal to H Ts minus T infinity. And if we substitute dt dx expression after finding out dt dx from here at x equal to L and equate it with H Ts minus T infinity, we will get Ts equal to T infinity plus q star L by H. That means Ts is a function of ambient temperature, uniformly distributed heat source, geometrical parameter, and film heat transfer coefficient or convective heat transfer coefficient. So this becomes the expression for Ts, that is surface temperature. And I am leaving a small task for you. You have seen what is the expression for Tx, you have seen what is the expression for maximum temperature, you have seen what is the temperature, what is the expression for surface temperature. From these three, please try to find out the functional relationship in the form of non-dimensional temperature, which is given by Tx minus T0 or Tmax divided by Ts surface temperature minus again T0 or Tmax maximum temperature. Having done that, we will take up a radial system. In the radial system, we will first consider a hollow cylinder, and this hollow cylinder, it is, in this hollow space, it is filled in by a liquid or a fluid which is having temperature T infinity 1 and the film heat transfer coefficient or convective heat transfer coefficient again H1. At R equal to R1 on the material, the temperature is Ts1, and R equal to R2, that means on the material surface temperature is Ts2, and local ambience outside this material is such that temperature is T infinity 2 and film heat transfer coefficient is H2. And again, this is 1D steady state heat conduction without any heat generation. So governing equation will be independent of theta, that is, basically theta direction, it is same, and independent of z, in the perpendicular to the plane, it is so large that any end effect can be neglected. Everywhere it is same, so it has only r variation. That is why we can write 1 by r ddr of kr dt dr equal to 0. The rate at which heat is conducted across any cylindrical surface. Anywhere, if we consider the cylindrical surface at any radius, this is given by twice pi r into L. L is the length of the cylinder. So QR is minus K twice pi r L, that is area, into dt dr. It is plain and simple Fourier's law. So we can write minus twice pi L into kr dt dr. And here we can see that from this equation, it is quite clear that kr dt dr is constant. So that means QR is twice pi L into kr dt dr. So QR is always constant at any radius. From the above two equations, it follows that conduction heat transfer rate QR is constant in the radial direction. Now from equation 1, again we can write kr dt dr equal to C, constant. So dt dr is, then we can write C1 by R, and T will be C1 ln R plus C2. So this is the temperature distribution in terms of C1 and C2, arbitrary integration constants, and we have to find out C1 and C2. And we apply the boundary conditions, which are R equal to R1, T equal to TS1, R equal to R2, T equal to TS2. We have already said R equal to R1, T equal to TS1, R equal to R2, T equal to TS2. So TS1 equal to C1 ln R1 plus C2, TS2 equal to C1 ln R2 plus C2. And from these two, we can write TS1 minus TS2 equal to C1 ln R1 by R2. So from here, we can write C1 equal to TS1 minus TS2 divided by ln R1 by R2. Now, after having found out C1, if we substitute C1 here, we will get expression for C2. So C2 is TS2 minus C1 ln R2. And C1 is given by this expression. We have simply written C1 ln R2. TS2 minus C1 ln R2. And then C2 has been found out. So if we can substitute now in our expression, that is T equal to C1 ln plus C2. So T equal to then C1 ln R, that C1 ln R plus C2. So C1, T equal to C1 ln R plus C2. This whole quantity is written here plus C2. So TR, general expression, the solution is TS1 minus TS2 divided by ln R1 by R2 into ln R by R2 plus TS2. This is the general expression which is function of R. Now, the temperature distribution associated with radial conduction through a cylinder, the temperature distribution, that means the expression of temperature distribution is a function of R and it's a logarithmic function. So we can see that radial conduction through a cylinder, the temperature during the radial conduction through a cylinder, the temperature distribution is logarithmic, not linear. As linear is for plane wall, so for radial geometry it is logarithmic. And so condition is the same, boundary conditions the same, but we can see distribution, internal distribution is logarithmic. Now the heat transfer rate is minus Ka dt Tr minus K. This is area twice pi R into L. And we differentiate with respect to R, expression for Tr, and we get Ts1 minus Ts2 divided by ln R1 by R2 into R2 by R into 1 by R2. And here we can see this R2 will cancel out, this R will cancel out. So we get QR equal to minus twice pi KL Ts1 minus Ts2 divided by ln R1 by R2. We can reorganize the terms and write it as twice pi KL Ts1 minus Ts2 ln R2 by R1. We absorb this minus sign, so it becomes ln R2 by R1. Therefore, now the conduction resistance we can write as potential difference minus heat transfer rate. So Ts1 minus Ts2 by QR is given by ln R2 by R1 divided by twice pi KL. So yesterday also we have done this in our last class, that potential difference divided by the heat transfer rate gives the expression for resistance. So expression for resistance, conduction resistance is ln R2 by R1 divided by twice pi KL. Now we can take composite walls. That means basically a cylinder which is having different layers of material, right? Here it has been shown, and typically when we are analyzing it, maybe we can have 3 such layers or 3 different materials A, B, C. So at R equal to R1, the temperature is Ts1, but this hollow space is filled in by maybe a heated liquid which is having temperature T infinity 1, and film heat transfer coefficient or convective heat transfer coefficient is given by H1. And at R equal to R1, temperature is Ts1, R equal to R2, temperature is T2, R equal to R3, temperature is T3, and R equal to R4, temperature is Ts4. And outside temperature is T infinity 4 due to the ambient fluid, and film heat transfer coefficient or convective heat transfer coefficient is H4. So, and temperature variation, you can see T infinity 1 is at a higher temperature, and from there we are getting the variation which is logarithmic variation within the material within which are basically radial shells, and These are A, B, C, radially arranged, or radial shells, material A, material B, material C, and temperature variation we can see. And finally, the outside temperature is TS4, and the ambient temperature in the material outside temperature is TS4, and the ambient fluid temperature is T infinity 4. And what we have already done in this case, if we try to find out heat transfer rate, we have to write basically the total temperature potential, that is T infinity 1 minus T infinity 4, divided by the conductive resistance and conduction resistance. Now, conduction resistance, in the last class we already we have learned about it, 1 by A1 H1. And what is A1? A1 means area 1, which is here it is twice pi R1L into H1. And now conduction resistance in radial geometry, from for material A, we can write ln R2 by R1 divided by twice pi Ka into L. Just we have done this in the previous part, in or earlier part. So, and then for material B, it is ln R3 by R2 divided by twice pi Kb into L. For material C, it is ln R3 by R4 by R3, sorry. For material C, it is ln R4 by R3 divided by twice pi Kc into L. Kc is the thermal conductivity of material C. And then again, outside convective resistance, and this outside it is convective resistance, and this is 1 by A4 into H4. And what is area 4? Is twice pi R4 into L into H4. So this is basically the total resistance. So QR equal to potential difference, temperature potential, divided by total resistance. We can, it is in series, so we can draw the circuit. T infinity 1, then the resistance TS1, again then the resistance T2, again between T2 and T3 we have resistance, T3 and TS4 we have resistance, and TS4 and T infinity 4 we have resistance. And these resistances are basically expressed by these expressions. So the foregoing result may be expressed in terms of, this can be expressed in terms of overall heat transfer coefficient. Just like convective heat transfer coefficient, we can coin overall heat transfer coefficient term, which is given by U1 A1 into T infinity 1 minus T infinity 4. So QR is, we have already seen, T infinity 1 minus T infinity 4 divided by the overall resistance, and this is given by T infinity 1 minus T infinity 4. This is overall resistance, this is total resistance. So T1 minus T infinity 1 minus T infinity 4 by total resistance. Again, this is the total resistance. This can also be written as U1 A1 into T infinity 1 minus T infinity 4. Then U1 into A1 is basically 1 by total resistance. So from there, U1 A1 equal to 1 by total resistance. Now A1 is twice pi R1L. We are bringing twice pi R1L in the denominator and simplifying the terms. So this becomes U1 expression. This is defined on the basis of inside surface area A1. I have already mentioned about it, of the composite cylinder. The overall heat transfer coefficient may also be defined in terms of A4. Then it will be U4 into A4 or any of the intermediate areas. And we can write A1, U1 A1 equal to U2 A2 equal to U3 A3 equal to U4 A4 and equal to basically summation of resistances, total resistance inverse, 1 by summation of total resistance. Now let us consider a hollow sphere. We have already done hollow cylinder. This is hollow sphere. Hollow sphere also at R equal to R1, its temperature is Ts1. At R equal to R2, its temperature is Ts2. Now again, this is also radial geometry, but this is also polar geometry, but spherical polar, not cylindrical polar. We have done cylindrical polar, and this is spherical polar. In spherical polar geometry, again, we in one direction, that means in R direction, we in absence of heat source, we can write 1 by R square del R of K R square dt dr equal to 0. And according to Fourier's law, again heat transfer rate is minus Ka dt dr. And basically that means QR equal to minus K 4 pi R square is the area at any radius into dt dr. And K R square dt dr, this part is basically constant. So if we consider here K R square dt dr into 4 pi, this is also constant at any radius. Now from 1 we can write K R square dt dr equal to constant, and dt dr is given by another constant C1 by R square. So Tr is given by minus C1 by R plus C2. If we integrate it once, minus C1 by R plus C2. So at R equal to R1, T equal to Ts1, Ts1 becomes minus C1 by R1 plus C2, and R equal to R2, T equal to Ts2. So Ts2 becomes minus C1 by R2 plus C2. From these two, we can get Ts1 minus Ts2 equal to C1 multiplied by 1 by R2 minus 1 by R1. From here, we can easily appreciate we will be able to calculate C1. So indeed we do that. C1 equal to Ts1 minus Ts2 divided by 1 by R2 minus 1 by R1. And having found out C1, our remaining task is to find out C2. So C2 becomes Ts1 plus Ts1 minus Ts2 divided by 1 by R2 minus 1 by R1 into 1 by R1. So now we can get the temperature distribution. That means Tr, we have already found out expression for C1, expression for C2, and then Tr equal to C1 minus C1 by R. So this is minus C1 into 1 by R plus C2. So Tr becomes Ts1, this just we rearrange the term, and we can write Ts1 minus Ts2 divided by 1 by R1 by R2, 1 minus R1 by R2 plus Ts1 minus Ts2 divided by R into 1 by R1 minus 1 by R2. So this is the expression for temperature distribution. And heat transfer across the wall, that is QR, is minus K 4 pi r square dTdr. So if we can find out dTdr from here, multiplied by minus K into 4 pi r square, we will get the heat transfer rate. So when we find out dTdr, basically this minus is after finding out the derivative minus k dTdr, we can see that this minus gets absorbed at plus, and of course rearrangement has also been done here. TS1 minus TS2, this is basically, this will be minus 1 by r square after differentiation. So and some rearrangement, we get basically 4 pi k TS1 minus TS2 divided by 1 by R1 minus 1 by R2. So the conduction resistance is given by 1 by R1 minus 1 by R2 divided by 4 pi K. If we express as temperature potential divided by QR is basically this term. So this is the resistance or conduction resistance in case of a spherical shell. Now we will work on critical thickness of insulation. So basically you can see again a hollow cylinder. Inside radius is R1, inside surface temperature is T1, and outside radius is R0, and outside heat transfer coefficient is H, and local temperature of the local ambience is T infinity. Now this problem indicates a possible existence of an optimum insulation thickness for radial system. This is suggested by competing effects associated with an increase in the thickness. In particular, although the conduction resistance increases with the addition of insulation, resistance increases means there is a possibility of heat transfer being less, but the convective resistance decreases. Convective resistance decreases means, again, resistance decreases means, there is a possibility of enhancement of heat transfer due to the increase in outer surface area. So there is a possibility of optimization, because one effect, adding insulating material, one effect is basically increasing resistance, that means reducing heat transfer rate. Another effect is decreasing resistance, that means increasing heat transfer rate. So if we basically try to find out the heat transfer rate, in this case this will be Ti minus T infinity divided by 1 by twice pi Lk ln R naught by R1, that this is basically conductive resistance of this cell, of this conductive resistance of this shell, basically cylindrical shell, and this is convective resistance, 1 by A1 into 1 by A1 A into H. So 1 by twice pi R naught L into 1 by H. So if we sort of again rearrange the terms, multiply both sides, the numerator and the denominator, by twice pi L, we get twice pi L Ti minus T infinity divided by ln R0 by R1 by K plus 1 by R0 into H. And then if we differentiate it with respect to R0 and set equal to 0, we get the condition for which this minimization can be done. So now let us try with this expression to determine the outer radius of insulation which will minimize the heat transfer. And for the minimization condition, dq dr naught equal to 0. We find out derivative of this expression, which is given by this expression, and we set it equal to 0, which gives R naught equal to K by H. So R naught, if it is set equal to thermal conductivity divided by film heat transfer coefficient, that is the condition for the outer radius for which we can minimize the heat transfer. So this introduces the critical radius of insulation concept. Up to this thickness of outer cylinder, the heat transfer will be increased by adding insulation. That's what I said. For outer radius greater than critical value, an increase in insulation thickness will cause decrease in heat transfer. So, if you add more insulation, heat transfer will be reduced. Now, conduction with thermal energy generation. This is yet another system. We will consider a radial system this is radial system, but not a hollow cylinder. This is a solid cylinder, and solid cylinder with thermal energy generation rate. That means uniformly distributed heat source. And we have written the governing equation 1 by R dt dr, R dt dr plus Q star by K equal to 0. We integrate once, so we get R dt dr equal to minus Q star by 2K R square plus C1, and integrating again we get the temperature distribution minus Q star by 4K R square plus C1 ln R plus C2. This is quite obvious, and here Q star is uniformly distributed heat source, and geometry is cylindrical, and angular symmetry holds good. So temperature distribution we have found out. Now we will apply found out in terms of C1 and C2. Now we will apply the boundary conditions to determine C1 and C2. Obviously, at the center dt dr equal to 0. This is basically this results from the symmetry at any diameter, right? We will get basically this symmetric condition, which gives us dt dr at r equal to 0 at center equal to 0, and T R naught is Ts. That means the surface temperature is at T equal to R equal to R naught. It is a surface temperature. Now, from the first boundary condition and equation 2, we have brought all three equations from the previous slide to this current slide. So this was our equation 2, and in the equation 2, the first boundary condition, if we set, we'll definitely get basically the dt dr equal to 0. We get C1 equal to 0 at R equal to 0. R equal to 0, dt dr equal to 0, so C1 equal to 0. Now, using the second boundary condition at R equal to R naught, T equal to Ts. So we get C2 equal to, that means C1 we have found out 0. So C2 now we can get from this equation Ts plus Q star by 4K into R naught square. So C1, C2 both have been found out. So we can write the expression for TR as Q star by 4K R naught square into 1 minus R by R naught square plus Ts. So we can rearrange the terms. We can write TR minus Ts equal to Q star by 4K R naught square into 1 minus R square by R naught square. This is the final temperature distribution within this on the cross plane, that means R theta plane of this cylindrical body. At the center line, T equal to T naught, that is we can say dTdr equal to 0, that is one thing, but this here temperature is also maximum temperature. So T naught equal to, then in this expression, if we substitute R equal to 0, we will get the maximum temperature, which is T naught equal to Q star R0 square by 4K plus Ts. So T0 minus Ts equal to Q star R0 square by 4K. So T0 minus Ts we have found out, and also we know what is TR. So from here we can find out a compact expression for non-dimensional temperature. TR minus Ts divided by T0 minus Ts is 1 minus R by R naught square. How does it vary with radius? Clearly indicated by this expression. However, Ts in the above expression is unknown. It can be related to ambient temperature T infinity from overall energy balance. That means Q star is uniformly distributed volumetric heat source into the total volume, that is pi R naught square into L, equal to H, the heat transfer coefficient, into the surface through which heat transfer is taking place, outer surface, twice pi R naught into L multiplied by Ts minus T infinity. So from here we can get Ts equal to T infinity plus Q star R naught by twice H. The foregoing approach may also be deployed to obtain temperature distribution in solid spheres, in cylindrical and spherical shells. So for solid cylinder, this is Ts equal to T infinity plus Q star into R naught by twice H. It's a surface temperature function of the ambient temperature, uniformly distributed heat source, geometrical parameter, and Film heat transfer coefficient. Now we will this we have found out, and now we will just extend this analysis. So solid cylinder we have done. If it is solid sphere, for the case of solid sphere, governing equation, I'm not deriving everything in detail. I'm skipping some steps. You may, since you have already done solid cylinder, so you can, fill in the blanks, so to say, the detailed calculation you may like to do. So this is the governing equation, 1 by R squared dt dr R squared dt dr, 1 by R squared ddr of R squared dt dr plus Q star by K equal to 0. And boundary conditions are again dt dr at R equal to 0, that means at the center equal to 0, and T at R equal to R naught, that means the surface of the sphere is Ts. So the solution will be T equal to Ts, T is function of R, is Ts plus Q star by 6K R naught square minus R square. and again maximum temperature that occurs at the center. So if we substitute R by 0, then we'll get maximum temperature, which is Ts plus Q star R0 square by 6K. And if the cooling at the outside surface is to a fluid at temperature T infinity via a heat transfer coefficient of H. So cooling at the outside surface is to a fluid at temperature T infinity via a heat transfer coefficient H or film heat transfer coefficient H. The overall energy balance will give Ts minus T infinity equal to Q star R naught by 3H. So same expression for solid cylinder we found out as Ts equal to T infinity plus Q star R naught by 2H. And for solid sphere it is Ts equal to T infinity plus Q star R naught by 3H. That is the difference. So this can be done now for cylindrical shells and also for spherical shells. That means hollow cylinders and hollow spheres. So I will stop here today. Thank you very much for your interest. Thank you very much indeed.